Welcome everyone. Let's wait for 5 more minutes to see if other people join. Then we can start. कौन कौन हाँ कौन है Okay, so I think we should start. So welcome everyone. Okay, let me allow that to go. So welcome everyone. This is NOC WA24 139 NPTEL tutorial on microelectronics devices to circuits. The course instructor is Professor Sudev Dasgupta from IIT Roorkee. I am Debashish Nandi from IIT Kanpur. So this is the prerequisites and we are now on week 9. Okay. So what we will discuss today is basically some uh, analog circuits and mostly touch upon how you calculate transfer functions and a detailed analysis on differential pair. Okay, so yeah, let's begin. So the question is that for the amplifier circuit shown in figure below, calculate the mid-band gain. Calculate the mid-band gain given this, and this. So can anyone tell me what do we mean by mid-band gain? Anyone? By the way, am I audible?
Yes, sir, you are audible, sir.
Okay. So can you tell me or try to guess what do we mean by mid-band gain? Just try out. What is the meaning of, just break down the terms that what I am asking is that what is this quantity, right? What do we mean by this mid-band gain? You can just break the terms and then try out. Mid means middle, then band means what band we are talking about, and gain of obviously you know that is V out by V in. So last time we had done one analysis on the how you calculate the transfer function or so-called the Bode magnitude plot, right? So if you just have your Bode magnitude plot, this is your log scale and this is your, let's say, AB. And what is the scale in the y-axis? The scale is decibel, right? And then if you see your gain versus frequency plot will look something like this, right? And these are your FH or omega H and omega L. What are these in the transfer functions? Omega H and omega L are poles in the transfer function, right? So what does this pole, where does this pole come from? And where does this pole come from? So we have seen that this comes from the coupling capacitances, right? And this pole comes from your CGD, CGS, and it gets amplified by the Miller effect. We have seen this in the last session. Okay. So what do we mean by mid-band gain is the gain in this region. So this gain we are talking about. So this is called AM. Let's say a mid-band. In the example, what we have discussed in last session, this pole was not present, right? So the characteristics was straight from DC coming up like this, and then it was going down here, and then we were encountering another pole. This was discussed in last session when we have ignored the coupling capacitances as was given in the problem statement. So this mid-band gain is basically your DC gain. Okay, DC gain of the circuit or DC gain of the system. So how do you calculate gain of this system? So, and what gain we are talking about? We are talking about small signal gain. Okay, these things we have discussed in detail in last two sessions. So how do you calculate this? One of the small signal representation what I have shown in the last class was something like this. So this is GM, and then it will go out. You have your RD here, and obviously you will have your, what is this resistance? This is your RDS or R naught of the device, right? The output resistance of the device, which will come between these two terminals, source and drain. This is your R naught. Fine. So now this is your V out, and this is your R signal, this is your RG, and what about the current? The current flowing in this direction is your GM times this voltage, let's say Vx minus 0 or GM Vx. Okay. So now if you want to calculate the gain, so how you can do that? If you just look at this output side, so what can you write? You can write that your V out is equal to minus Gm times Vx, that is your current, and this current is flowing in a parallel combination of your R0 and RD. Is this much correct?
Yes, sir.
So now, but you wanted to find out the relation between V in and Vx. So what is Vx in terms of V in? What is Vx in terms of V in? It is simple resistive divider, right? So it is simply your Rg by Rg plus R signal. And how can we write this thing? Because what is the current going into this terminal? So by the way, what is this terminal? This terminal is your gate and this terminal is your source, right? So what is the current going into that terminal?
0.
So if there is no current, then I can simply remove this. So now can you tell me what is Vx in terms of V in?
चलो तो आप लिख ही दिए हैं.
Sorry,
Sir, RG divided by RG plus.
Rg divided by Rg plus R signal. You have understood this, right?
Yes, sir.
So the reason is that because there is no current going inside this terminal. So that is why you can use the voltage division through a voltage divider easily. So now what is your V out? Your V out is now minus Gm times what is Vx? Vx is your Rg over Rg plus R signal times V in times your R naught parallel Rd. So your gain is minus Gm times Rg over Rg plus R signal times parallel combination of the resistance at the output. So if you calculate this, it will come out to be minus 26.67. So what are that? GM is given, right? GM is given as 4 into 10 raised to minus 3 ampere per volt. Then your RDS is also given 40. Your RD is also given, and RG given, R signal is also given. So all the quantities in this equation are known to you. So you can easily calculate that. Okay. So this is what is meant by mid-band gain, because if you ignore your coupling capacitances, always remember that this mid-band line will touch the DC line. So this is omega equal to 0. Omega equal to 0 means your DC. Your frequency is 0. That is your DC. So your DC gain is the mid-band gain. Okay. So let me use consistent terminology. AM. Okay. So let's move on to the next problem. So in a BJT based differential amplifier, the allowable range of VCM is determined upper at the upper at the upper end by Q1 and Q2 leaving the this mode and entering this mode. Okay. So first thing is that in amplifier circuits, BJT needs to operate in which region?
Saturation region.
BJT is, so if this is my VCE and let's say this is my IC, so it will be something like this. So which region I should operate? The right one and the left one, which one? This region or this region? The right hand side region or the left hand side region of this dotted line for amplification?
So right hand side,
So what is that called for a BJT?
active region.
And what is the saturation region for BJT? This is the saturation region, right? So why did someone say that BJT should be operating in the saturation region?
सर MOSFET सर वो
Yeah,
इंटरचेंज
exactly.
हो
So
गया
you should be
जल्दी होने
careful,
का.
right?
Yes, sir.
In MOSFET, the terminology is a little bit different than in case of your BJT. So in linear active region, your device has to be operating. Okay. So that is the first case. So as soon as my device come out of this linear region, so no longer my small signal analysis will be valid. So as soon as BJT bias comes out of linear or active region, let's say, or let's say forward active region, small signal analysis fails. No longer an amplifier. Okay. So that determines what region I should operate. Okay. So now think in this way that let's say you are biasing it like this. There is a small signal. Let's say this is your V1 and this is your V2 and this is the common mode bias. Okay. Which determines that your device is in this region. Fine. Now you are asked to find out that what is the upper limit of VCM. Okay. So that means what? You are increasing your VCM. Okay. So what will happen? VCM is increasing means this bias is increasing and this bias is increasing. That means what? Your VBE is increasing. And what will that increase? If your VBE is increasing, what will that increase? In a BJT, if your VBE, base to emitter voltage, is increasing, that will increase your IC. Do you remember this formula? IC is equal to saturation current times exponential VBE by VT.
Yes,
You
sir.
remember this, right? So if you're as soon as you increase your VBE or your VCM, so your IC increases. So this current increases. This is your IC. Now what happens when IC increases? The drop across this increases. Drop across resistances increases. Is that okay?
Yes, sir.
So now think in this way. Now this is your VC, right?
Right.
So if drop across this increases, what will happen to VC? Will VC increase or will VC decrease?
DC decrease.
Why VC decreases? Because VC is equal to your VCC minus IC times, let's call this resistance as RC. So IC times RC. So this quantity is your increasing. So obviously your VC will decrease. So that means your VCE decreases. So now focus in these two. So in this configuration, if your VBE increases, your VCE decreases. Okay. Now, remembering this, look at this now. So this is your VCE and this is your IC. I am assuming that both the transistors are matched. So I am drawing just only one curve. Okay. You read it as IC1 versus VCE1 and IC2 versus VCE2. The same thing that will happen in both the branches. By the way, this is called, this entire stuff is called one branch. This entire thing is called one branch. And this is called another branch. Okay. So now, how does your characteristics look like? So this is for, let's say, VBE1, VBE2, VBE3, VBE4. Okay. And your VBE4 greater than VBE3 greater than VBE2, VBE1. So now let's assume that initially your device was biased in this point. Okay. Now as you increase your VBE, as you go to this curve, so your VCE will decrease. So now let's say your bias shifts to this point. Then your bias will shift to somewhat this point. Then your bias will shift to somewhat this point. Do you see this shift? As you are going up, your VCE is increasing in this direction. In the left side, VCE is decreasing. So now, when your device was in this place, it was into forward active. Now, as you are increasing your VBE, your VCE is shifting left side. So now, latest your device has come into this point. So this is what? This is your saturation. That means your transistor is acting no longer as an amplifier. So when your BJT based differential amplifier allowable VCM determined by the upper means at what value it will actually leave the saturation region. That means if you just draw your this curve, so even at VBE you are in your linear region. Okay. So this is called what value means. Let's say now if I draw a line where this is the bias point. So at this VBE, let's say this VBE 2A. So at this VBE, you till this VBE you can increase your VCM. Okay. Beyond this you cannot increase because your transistor is going into saturation region and coming out of forward active region. Okay. So Q1 and Q2 leaving the forward active region or forward active mode and entering in the saturation mode. Okay. So this will be your right answer. So have you understood this?
Yes, sir.
Okay, good. So this is what is happening. Now let's move on to the next point. For a perfect matched differential pair, the common mode gain should be this and CMRR should be this. Okay. So let's just copy this. Okay.
सर मॉसफेट का एग्जांपल लेके बताइए इसको.
MOSFET का एग्जांपल. ओके. MOSFET I was saving for a later time, but if you want, then that is fine also.
बीजेटी कोई पूछता नहीं है ना.
Okay, then there is no issue because this is how your MOSFET differential pair look. I will explain in detail today, okay, how MOSFET differential pair has come about and what are the steps you should understand to understand a how the differential pair of a MOSFET works. So please hold on till then. So this is what? This will be your some VCM plus V1. This will be some your VCM plus V2. Okay. And let's say you have some resistances here. Let's say this is your supply rail or VDD. Okay. So what is CMRR? What is the full form?
कॉमन मोड रिजेक्शन रेशियो.
Common mode rejection ratio. And how does that, how is it defined? It is basically your AD over AC. Okay. What is AD? AD is the differential gain and AC is the common mode gain. Okay. What does differential gain and common mode gain means? In common mode case, you apply same voltage, or let's call it only VC, let's say. You apply the same voltage and you take the output, let's say it is a fully differential amplifier. So you will have one output here, you will have one output here. So your gain is defined as VO2 minus VO1 divided by your VC. So if two branches of the differential pair is perfectly matched, what can you say about V01 and V02? It will be equal.
Yes sir.
So what is your AC? Your common mode gain is 0.
0.
And what about your differential mode gain? How that is defined? That is defined as, let's say you are applying some V1 here and V2 here. So it is defined as V02 minus V01 over V2 minus V1. Okay.
Okay.
So that is generally non-zero because your this quantity and non-zero and non-infinity, because this will be different because your inputs are different. So that will be a finite ratio. Okay. So now what is your CMRR for this case? Your AC over AD or just the opposite, AD over AC?
0.
So AD is what? AD was some non-zero, let's say some GM equivalent, let's say it is some GM equivalent times R out equivalent. It will be in this form only. Modulus of that, divide by 0 for a perfectly matched pair. So it will be your infinity. Okay. So
Yes,
for a
sir.
perfectly matched case, your common mode gain is 0 and your CMRR is infinity. So your common mode gain is 0 and CMRR should be infinity. Okay. So this question does not concern about what is your if it is BJT or if it is MOSFET. Okay, as long as both the pairs are identical, that means you have your AC equal to 0, but that is very difficult to make. Okay, that we will discuss later why it is difficult. And your CMRR is infinity. Your CMRR generally gets a very high value around your, let's say, 5,000, 6,000 range of value, and your differential mode gain also plays a very big role in that. And common mode gain is generally not 0 always. It is a very low value but not 0. Okay.
Yes, sir.
Okay. So moving on to the next problem. The input impedance of a common drain stage is dash than that of a common gate stage. Okay. So we have common drain, we have common gate. So how will your common drain stage look like? Here you will take your output. Here you will give your input, and this will be in small signal sense. This will be, let's say, ground. Small signal ground. Okay. So what is the input impedance? Looking in, what is the input impedance? So for that, what you need to do? You connect a,
So that is infinite now.
exactly
Open,
right. So
open
why did
circuit.
you take time? It is V test. So no current is going out. So that is V test by I test. That will be your infinity. And what about your common gate stage? So let's say this is small signal ground, and let's say this is drain, this is source. You are giving a swing here and you are taking some output here. Okay.
Yes, sir.
So what will be your input impedance?
RDS plus RS plus gain of the amplifier.
It is generally your R on of the device in on state and R off in the off state. Okay, off and on means your this is on or this is off. Okay, you are applying some signal, so this signal has two paths to flow. One is the channel resistance and one is the RDS of your device. Okay,
Yes, sir.
so what is greater? So common drain input impedance is always greater than common gate input impedance, and this is because of the fundamental fact that in case of common drain, the gate is seeing the input. Okay.
Yes, sir.
Okay. So let's move on to this problem. Okay, this is where we'll analyze the differential pair. Okay, so be more involved in discussion of this problem. So they wanted us to find out the differential, the gain of the differential amplifier. Okay, so we'll go for this problem very slowly. Okay, so first thing, why do we need differential amplifier in the first place? We need to understand it from the very basics, that why it is required and how it is made with the tools what we have already. So why do we need differential amplifier? What is a differential amplifier? Differential amplifier is basically your what? Your output will be difference of two input and some amplification factor, right? This is what is differential amplifier.
Yes, sir.
So can you tell me think about a situation where this is required? Think about your control systems. Just let me draw and you tell me if you remember this thing or not. Let's call it gain only. Do you remember this thing?
Yes, sir.
What is this?
Feedback, uh,
What kind of feedback?
negative feedback,
So why is this required?
uh, and to stabilize the system.
How do it stabilize the system?
If positive, there will be a oscillation.
That is fine, but
Oscillate.
why does it require
Uh,
stabilization? Means how does it stabilize your system? Give an practical example.
like you switch on the AC and
Okay,
set the temperature 22.
okay,
If difference is room temperature is 27, then
okay,
it gets the difference of 5,
okay.
and then it will a circle will complete, then automatically it will come to 22.
So basically, you mean to say you want a fixed temperature, right? That is your desired temperature. Let's say that is 27 degrees Celsius, or that is not practical. Let's say you want 24 degrees centigrade, right?
Right.
You want to fix the room temperature at 24 degrees centigrade. Now you switch on the AC, so AC will start cooling. But can it exactly fix your temperature at 24 degrees Celsius? No. So what it will do, it will then first put your temperature at, let's say, 22. It starts cooling and it puts your temperature at 22. Then you see, you feed it back to the loop and measure the error that, oh no, my temperature has gone low. So it will automatically get this is what, this is your error. So it will get the error signal and again fit into the loop. Understood? Same
Yes, sir.
thing, you can think that you are riding a motorcycle, okay? Or you are riding a scooty. So you want to, have seen that in the roadside, the signal is that you cannot speed up more than 40 kmph. So you want to maintain that 40 kilometer per hour mark. So you start your accelerator. So it is not possible for you to just put the accelerator and fix it at 40. Initially, when you start accelerating, it will may go to 42, 43. Then your eyes will act as a, and the meter and the speedometer will act as a sensor there, and it will show you that no, you are exceeding the limit. Then you will just slow down the acceleration. Then it will come down to 38, then you will again put it to 41, then maybe 39, and so in that sense you come at a speed, you can, so that you maintain the 40 kilometer per hour mark. So this sense of feeding you back by the speedometer through your eyes is called the negative feedback. That gives you the stability, and the stability in a sense that you maintain your desired output at 40 kmph. Okay. So now this block, how do you, this block and this one. So this is what basically, this is, let's say this signal is V1, this signal is V2, and this is your AD. So this entire block is representing the same thing.
Yes, sir.
Is it not?
Yes, sir.
So if this is your V out, so this entire block is essentially giving you the feel of a differential amplifier. So this is one example where your differential amplifier is required. Okay. So let me give you another case. So let's say this is M17, this is M2, this is M1, and these are the transistors, and this is your wafer. Okay. So do you understand this plot? If not, I'll explain. So
Yes, sir.
what
On
is
a
this?
wafer.
So on a wafer, you will have multiple ICs. Let's say this is IC1, this is IC2, this is IC3, this is IC4, and so forth. Okay. So let's say this is for purpose 1, this is for different purpose 2, this is purpose 3. So what do you think, how the source and drain contacts are connected? This is the top view, and this is the cross section. Okay. So let's say this is one wafer you have, and there is one transistor sitting here, another transistor sitting here. These two transistors have very different purposes. Okay. Let's say these are the metal vias from your source and drain, and again these are the vias from, so there will be other contacts also from gate also. Okay. So now these two, let's say one you are connecting to Let's say both are NMOS. This is also NMOS. Okay. You can use PMOS also in the same substrate by the twin tap technology what you have read in this course. Okay.
Yes, sir.
So let's say you want to, this is your ground line. Okay. So you want to connect your sources to that. Let's say your source is connected here. Your source is connected here. But you want to have two different power supplies for both the transistors. Let's say one you want to operate at VDS equal to 1 volt. Another one you want to operate at VDS equal to 3 volt. Okay. So what will you have? You will have a metal layer coming here. Let's say this is your M1 dedicated for this NMOS 2, and this is connecting to your, let's say, M5. Okay. Metal layer 5. So in ICs, what is happening that there are multiple transistors, and all the transistors for all the purposes will have to have different types of voltages. So if you supply all the contacts through the same metal line, so it will get shorted, it will not work. So you need to have multiple metal lines crossing on top of your transistors. So how will you cross those metal lines? You do that, or people do that by putting the metal layers one above another. Okay. So this is called multi-level metal wiring. So at the ground level, think it of an, it's like a multi-story building. Okay. At the ground level or at the bottom, you have your transistors. Then at the first line is mainly dedicated to your polygates. Then you have multiple in nowadays transistors. It has metal layers till 19, metal layer 19. You can think of that, how many billions of lines are crossing over one another in a crisscross way. One maybe for your digital application, one transistor is being used for digital application, another transistor is being used for analog application. Okay. I'll share a link at the comment section of this video when I'll post it. There you will see that how this metallization and all this happening in the industry. So you will get a more physical feeling of it. That is not for the course, just for you to visualize that how the things are working in the actual IC. Okay. So now can you tell me why did I, in this context, why did I put this, the cross section of this metal layers, this metal lines actually? Okay. The cross sections very high, and in the, as we go down, the cross section is getting lower. Why does this happen? You should use common sense that cross section of any wire, what does it directly determine, directly related to its resistance, right?
Yes, sir.
As your metal layer 17 is far away from the transistor, so there will be series resistance drop because of the length distance it has to travel, the signal has to travel.
Yes, sir.
So how to compensate that?
Thick
Your
wire.
R is equal to rho L by A. So your L is increasing as your metal levels are getting higher. So you need to just increase the area, or you need to make the wires more fatter. Okay.
Yes, sir.
Okay. If you have given this context, so what happens actually in the ICs? Let's say this is a metal line or metal layer. Let's say this is your M5, which is carrying digital signals. Okay. So this course is if you have noticed that This course is inclusive of both digital and analog applications. Okay, this is not a pure digital, pure device, or pure analog course. This is a combination of all these things. That is why I am giving this example. Otherwise, I would have avoided this. So let's say this is a digital line. So what is the kind of signals digital lines carry? Let's say this is your digital line. And on top of that, let's say another metal layer line is passing like this from C to D, and here is your some analog signals. Some analog line is crossing. So what is the digital? How does the digital line carry the signal? Means what kind of signals it is? If I draw the waveform,
Discrete, discrete signal.
not
Just
discrete, it will be like
square wave.
this pulse, right?
Yes, sir.
So what is the frequency of this pulse? Means how much frequency? Let's say if I give you this kind of transition. So what do you think? Is an instant switch? What is the frequency? Very high or very low?
Very high.
Switching frequency is almost infinity, right?
Yes, sir.
So don't you think that this will create a coupling capacitances through the dielectric in between, because between these metal layers there will be SiO2. Okay?
Yes, sir.
So don't you think that at this high frequency these two lines will be coupled to each other?
Yes, sir.
You got this, right? These lines will couple to each other, because
Yes, sir.
when two metal lines are in parallel or any angle, if very high frequency signal is crossing to them,
Coupling
so
capacitor is there.
see, earlier also there was capacitance, right? Let's say the capacitance was j omega c. So now omega is increasing, so your x is decreasing or the impedance is decreasing. So now signal will start to leak from these paths also. That is what we mean by coupling. Capacitance is always there. Earlier it was acting like an open circuit in small signal, in low frequency signals. Now it is acting like a short circuit, or signal path. Signal can leak through this path. That is what coupling means. Okay.
Yes, sir.
Now if you have understood this much, now let's say your analog signal, what you are desiring is this. This is your desire. But now you are getting some distorted signals. Distorted analog signal due to coupling from digital line. So can you point out what is the exact reason of this and how we can get away with this? The reason behind this is both analog and digital lines are referred to a, or referenced, the reference ground is a global ground. Okay, referred to a global ground. So let's say this, if this voltage is VD, so this is with respect to this ground VD, and if this is VA or V analog, this is also with respect to this ground. Now if I can make my analog signals reference differently, then this problem we may get away with. We'll see how. Let's take the same digital line. Let's say this is A, this is B, and some switching signal is it is carrying, and I have now let me put two analog lines. Okay, let's say this is CD and this is EF. Fine. Now what we have, let's make this as the reference line for the analog signal. Okay, so now this line will also get coupled to the digital line, and this line will also get coupled to the digital line. So if you have a signal something like this, and this, let's say this was your ground, so this will also have some distortion, same level of distortion, because these two lines are very close to each other and they are seeing the same digital line beneath them. So now if you can take these two and pass it through a difference amplifier or differential amplifier, so this is your VA, now this is your VLG, let's say local ground. So now what will be your output? Your output, you will get a clean signal
Yes, sir.
because your distortions gets cancelled.
Cancel.
So in these cases, that is why in your IC environment, it is always suggest to apply your input signals in a differential sense. Okay, that's why we prefer differential input signals. Okay,
सर ये डिस्टॉर्शन जो प्रीवियस डिस्टॉर्शन एंड आफ्टर आफ्टर पासिंग थ्रू द डिफरेंशियल एम्पलीफायर दोनों
yes,
सेम कैसे होगा?
no, this is same, right? Let's say your this is your VA plus your distortion, you are having delta V. So this is what? This is your ground. Okay, plus delta V. So this delta V gets negated, right?
सर डेल्टा वी, सर दोनों का डेल्टा वी डिस्टॉर्शन होगा, ये मतलब आप कैसे इंश्योर कर रहे हैं?
Because these two lines are very close to each other and it is seeing the same coupling line. You understood, right?
यस सर,
So
यस सर.
this is what? This coupling, this distortion is due to what? Due to the digital line on the analog line, right? Now you are having the same distortion from the digital line to another analog line, which is very close to this.
यस सर.
So this will see almost similar levels of distortion.
ओके, यस सर.
Okay, so if that is the case, now so far what we have studied, can you tell me if I can use my common source amplifier as differential amplifier? So what is your common source amplifier? So this is your, let's say, V1 and this is, let's say, V2. So what is your V out? V out is equal to minus GM times RD times V1 minus V2. Is that clear?
यस सर.
Now can you tell me what is the problem with this? Ideally what we wanted? We wanted something like an ideal op amp, right? So what is the purpose of studying differential amplifiers or differential pairs? We can easily do this with the common source amplifier itself. By the way, what are the characteristics of this op-amp for an ideal op-amp? What is the input resistance at these points?
Infinite.
What is the input resistance at V1 is seeing? Yes,
Very less resistance.
very.
Less resistance.
Why V1? What is the resistance?
V1 very high, very high. Output resistance very less.
V1 is seeing almost infinite resistance, right?
Yes, yes, sir.
What is V2 seeing?
A resistance through drain, some finite value.
Not drain, it is seeing through source, right?
Source, sync through source,
So
some
how do
finite
you,
value.
yeah, so what is that? How do you calculate that? You put this grounded, you put a V test here, right?
Yes, sir.
And you have your RD here. So this is your I test. So what is this current? This current will be GM times V test. Fine. If you ignore your R out, then what is your R out? It means R out of the, if you ignore this R out, if you ignore this, then what is the V test by I test? That is your 1 over GM. Is it okay?
Yes, sir.
So you are seeing 1 over GM, right? So that
Yes,
GM is generally your a high quantity.
yes, sir.
So this will be
Low resistance,
not
low quantity,
not infinity. Let
not
us say
infinite.
in that sense.
Yes, sir.
But why does this matter? Why does input resistance matter? So basically, what I am trying to get at is that you have something like this, right? This is your, you are taking this as your V1, this as your V2. Okay. So why do you think this V1 and V2 is coming from? Are you applying it directly or it is coming from some previous stage?
Coming from some previous stage.
So that previous stage I can model as, okay, just let me explain a further detail. Let's say it is coming from another amplifier, okay? And let's say this is also coming from another amplifier or some previous stage. Some previous stage 2, some previous stage 1. So this I can model, this I can model as, by removing this, I can simply model this as some voltage source with some series resistance, right? This is the R out of my previous stage, and then this will be the input resistance R in. Okay. And in this case also, let's say it is coming from some previous stage. So R previous, and this will be the, I can simply disconnect this two, and this will be my R in 2, R in 1. So I want what? And let's say this was my V1 and this was my V2. So output resistance of the previous stage and input resistance of the current stage. So I have two options. Make output resistance of previous stage equal to 0, or make input resistance of current stage equal to infinity. Okay. So what will happen if I make output resistance of previous stage 0? That means I will just short this thing. That means this entire V1 will appear at here. Similarly, if this will get shorted, so entire V2 will appear at here, which is what we want, right? Is that okay? Or in other word, this is one possibility. Or in other word, we want to make sure that my input resistance of the current stage is infinity. That means what? That means this becomes open circuit, this becomes open circuit. What does that mean? This V2 will again appear here and V1 will again appear here. So I have these two options, okay? So what I am designing now, is the current stage. So I have to make sure that the input resistance of the current stage is infinity. So did you get that?
Sir, in short, you sum up what you said.
So what is happening that my voltage V1 and V2 that is coming from previous stage, okay?
Yes, sir.
And previous stage has some output resistance that will come into series to that voltage because of the Thevenin equivalent.
Yes, sir.
So that is what? That is your this R out previous, okay?
Yes, sir.
And now I can entirely remove my this stage and model it with an input resistance. The input resistance of this terminal.
Yes, sir.
So I want what? I want this entire V1 to come at this point at the gate, right?
Yes, sir.
So for that I have two options. One is that make the output resistance of the previous stage 0. What will that make? That will just short this and this V1 will appear at this node
Yes, sir.
irrespective of the value of R in 1. And what is the other option? Other option is that you do not care about what is the output resistance of the previous stage. You just make this one infinity. If this
Yes.
one is infinity, then this voltage will appear at here.
Yes, sir.
So in case of MOS common source amplifier, the gate resistance gives you that infinite input resistance.
Yes, sir.
But similarly, this V2 has to come to this point at this node.
Yes, sir.
For that,
But so,
either my R previous has to be 0 or R in has to be infinity, right?
yes, sir.
So I am designing the current stage. So I am not bothered about whatever the previous stage and whoever has designed the previous stage and how they have designed. I am bothered about, I want my current input impedance of the current stage to be infinity. Is that okay?
Yes, sir.
So this is the same thing what we have discussed in our first lecture, that is loading effect. So
Yes, sir.
how to get rid of the loading effect?
Yeah.
So this is your, let's say this is your V out. So can I use a buffer at this point and apply my V2 from here? So now if I look at this terminal, what is the input resistance?
Infinite.
Because my buffer, ultimately the input will be at some gate terminal,
Yes, sir.
and again, so I am getting a V2 here and V1 here.
Yes, sir.
So do you understood, have you understood the issue?
Yes, sir.
So
Input resistance is finite.
exactly, I want the other terminal of my common source amplifier, the source terminal, I want to make the, looking into the source terminal, I should see infinite resistance. The way to do it is that connecting a buffer, the same thing what we have done in case of avoiding the loading effect earlier.
Yes, sir.
So how, what is a buffer basically?
Whose gain is 1.
No, what configuration we use?
Uh, what configuration? Common drain.
Realized by common drain, right?
Yes, sir.
So how does a common drain look like? Common drain looks like this is your input, this is your output, and this is the common part of the thing, right?
Yes, sir.
So we will just, so this is your V in, this is your V out. In our case, this is my V out of the buffer and this is the V in of the buffer. Okay, we will just connect this block here. So now see, if I draw my circuit like this, do you recognize this or not? Do you recognize this?
Yes, sir.
So you see how the bottom part of your differential pair come about.
Yes, sir.
This is nothing but, so let us now start naming the transistors. So this is your, add a few more pages. So this is your amplifier stage and this is your buffer stage for input V1, and similarly, oh sorry, for input V2 for say. Similarly for V1, this will act as a buffer stage and this will act as an amplifier stage. So M1 and M2 basically creates a combination where your these two acts as amplifier and buffer to one another. Okay.
Yes, sir.
Now, how do you want to bias this? So you have this. So far you have this. So let's say this is V1. This is V2. I am just omitting the series resistances. So what do you want to see in the small signal sense at this node?
V1 minus
This
V2.
this entire current should go to this path and come out of this V2 V out. So
Yes,
you
sir.
want to see an open circuit because otherwise there will be a current flowing through this path. See, you want R in small signal infinity at the bottom.
Yes, sir.
And how do you do that? So if you want to bias it in the small signal, what shows you an infinity impedance?
Gate.
No, no. In ideal terms, ideal circuit component terms.
Open circuit. A
So
current source. Yeah.
if I apply a current source, so it will show me
Open circuit.
at the small signal sense, right?
Yes, sir.
So how do you realize this current source? So another question is that in an IC, you need many current sources, okay? How do you realize those?
Another MOSFET.
So you realize actually you create a master current source, okay? One current source that is your off chip. Off chip means outside your IC. So now I want this current source to copy. So I will just do what? I will use current mirrors. So this entire thing will give me, if I look into this terminal and if W by L of this and these are matched, so I can get a I0 here.
Yes, sir.
This is your
Current mirror.
current mirror, right? So if you see, in many cases, you will be your differential amplifier will start looking like this. So this will be your master current source, and then you will just see that this is your V1, this is your V2. On top of that, we will discuss now. So you have seen circuits like this, right? In your assignments.
Yes, sir.
So don't worry, this is nothing but you can replace this entire thing with a current source, the value of this. But you need to be careful about the W by L ratio. By changing the relative W by L ratio, you can get various ratios of currents, right? Various fractions of current or multiplications of current. Okay.
Yes, sir.
So that is one thing. Now let us discuss what should be on the top side. How should you bias that? So far we have seen this is I0, this is V1, this is V2, M1 and M2. So M1 and M2 are matched. Why they are matched? Why do we match M1 and M2? because in a case of an op-amp, these two terminals you have to, when you see for an ideal op-amp, these two terminals act equally same, okay?
Yes, sir.
Just a change of sign or a
Yes,
180-degree phase shift. Apart from that, these two terminals should look exactly the same. So if M1 and M2 are matched, so can you tell me what is the current flowing in these two branches?
is there any current?
No, your DC current has to flow, right? Let's say something is connected to that. Irrespective of that, what is the current DC current coming from these two branches?
Zero.
No. Apply KVL at this node, KCL at this node. This should be I0 by 2, right? I have a current source here and I am telling you I have two branches. Let's say this is same, this
Yes,
is
sir. I
same.
by two, I by two. Same.
It will be
Same
I0 by
resistance.
2, right?
Yes, sir.
So if this is I0 by 2, so I can simply, okay. Now what is the small signal current? Due to presence of V1, there will be a small signal current. Let's say I1, and due to V2, there will be a small signal current I2. What is I0 by 2? I0 by 2 your DC current. Okay.
Yes, sir.
And I1, small I1 and small I2 are the AC
Small
currents
signal.
that is flowing due to small signal currents that is flowing due to the V1 and V2.
Yes, sir.
Now what do I want? I want this entire thing to take out of this terminal and connect it to some load resistance. So my V out will be what? GM times RL times, what is this current?
So which current you are asking for?
I am asking this current. What is this current? Is it not I1 minus I2? The small signal current, or let me just maintain the color. So is it not I1 minus I2?
Yes, sir. That is I1 minus I2.
That is I1 minus I2, right?
Yes, sir.
So you want this entire I1 minus I2 to flow in this branch. So what you do, again the same thing. Looking above, it should see a small signal infinite impedance. So the way to bias this is, this is your V1, this is your V2. So what is the value of this current source should be? This DC component is I0 by 2. This DC component is I0 by 2. the AC component is I1, the AC component is I2, the AC component coming out is I1 minus I2. So in the AC sense, it is an open circuit in the AC sense. But in the
Yes.
DC sense, it has to be
I0 by 2.
exactly, it has to be I0 by 2, right?
Yes, sir.
Now, if this is I0 by 2, and what if this is not I0 by 2?
Biasing is not proper. Come
Biasing is
in
biasing
linear
is not
region.
yeah, exactly, absolutely right. If you have understood this, then that means you have some good understanding. If this is not I0 by 2, then what is happening basically? Two current sources. So let's say this is some delta I. So this delta I will flow through some parasitic capacitances and charge this. Okay. So this node will start to increase. Or if this is more, then this capacitor will discharge and then this will come out of saturation.
Yes,
Okay.
sir.
Two cases can happen. So now this is your I0 by 2. Okay. Now let us see the small signal gain of the circuit. So you have so far this is your GM1. So let's say this is your M1, this is your M2, this is V1, this is V2, and this will be small signal open, this will be small signal open, and this is your V out. Okay.
Yes, sir.
So what is the resistance seeing this side?
Sorry. ZM GO1.
So again, one thing, you have a transistor, you are looking into that. Okay, you are looking into this terminal and you want to find out the input resistance. So what you will do, and this is your G01, you will just short the input. That is how you calculate your Thevenin resistance, right? You
Yes, sir.
short all the voltage sources or null all the voltage sources. So what you see a path of current flowing here and another path is flowing here, right?
Yes, sir.
So if you connect your V test, so this current I test will flow through this path and this path. So which resistance is your higher resistance? Output resistance or 1 over GM? This is very high value, right?
Okay.
Because you see your curve is almost flatter at this point. So
Yes,
this is
sir.
almost like an open circuit. So
Yes,
most
sir.
of the current will flow through this path only. Even if you do the small signal analysis and find out the input resistance, you can safely see that you are looking at 1 over GM1
Yes, sir.
after this node. So now you can, this is your M2, this is your G02, and this onwards you will see your 1 over GM1. Okay.
Yes, sir.
And this is your V out. And this is your G02. Okay.
Yes, sir.
So now if this is 1 over GM1, what is your, let's say, what is your equivalent GM? How do you calculate your equivalent GM? Yes.
Same test, take a test voltage and flow the current.
Take care. So let's say this is your V2, right? So what is this? What is this current? If this
V2
is your
will be,
Vx, and let's say if you ignore this output resistance, so what will be this? This will be V2 minus Vx times GM1,
yes, sir.
or in that matter, let us not equate it now. It will be GM2 for that matter. This current will be equal to what? Your Vx by, or Vx times GM1. This current is equal to this current. So what is this current? This voltage difference times the GM of this is equal to this. So your V2 times GM2 will be equal to what? Will be equal to your Vx times GM1 plus GM2, and your GM transistors are matched. So what will be your Vx? Your Vx will be V2 by 2. And what is your I2 then? Let's call it I2. I2 will be your V2 by 2 times GM1 from this equation. Similarly, if you analyze your other branch, let's say this is your V1 and this point is your Vx, right? This is your Vx. Beyond that, you are seeing 1 over GM1. That is why you have put it 1 over GM1. So in this case also you will see 1 over GM2. So one current will flow here and this is your Vx. So similar way, if you find out your I1 will be V1 by 2 times GM1. So what is the current or the short circuit current flowing out at this terminal? That was I1 minus I2, right? So your I1 minus I2 will be GM1 over 2 times V1 minus V2. Is that okay?
Yes, sir.
So if that is okay, what is your R out? So this is your, you apply your V test here, you do this ground, you have this grounded, you have this resistance and you have this resistance, and this is your Vx. So can you calculate your R out? Yes. Tell me, how do you calculate your R out? What is looking into this terminal? What is the resistance? This we have discussed right now, right? Looking into this is 1 over GM1. So I can simplify this circuit as this is my M2, this is my M1, this is my M2. So this is my 1 over GM1. This is my G0. Let's write GM1 only. It is the same thing, conductance. GM1. So it will be G02, and you are applying a V test here. So you calculate your I test. Okay. So this is your Vx. So your I test is equal to Vx times GM1, because this current has to be equal, the entire I test has to flow down also. So your Vx is what? I test by GM1. Now applying KCL at this node, you will have your I test equal to this current V test minus Vx times G02 plus the current in the through the transistor, and that is minus Vx over times GM2. So your I test is equal to V test times G02 and minus Vx times GM2 plus G02. And what is your Vx in terms of I test? I test by GM1 times GM2 plus G02. So that is your I test 1 plus GM2 plus G02 divided by GM1 equal to V test times G02. Okay, you got this much?
Yes.
So now if you take your V test by I test, this quantity will be how much? Any idea?
No, sir.
This quantity is how much? This GM1 and GM1 is same, right? This is I test by 1 plus, this is 1 plus G02 by GM1 is equal to V test times G02. So this quantity, what do you think? It is greater or lesser? G, always remember that your R out is almost infinity, right? R out of any transistor, if CLM is or channel length modulation is not present, then R out is infinity. if channel length modulation is present or your curve has some slope, so it will be Rout will be very large
Large.
value. So what is your G0?
Very large.
Very small, right? 1 over R0 is G0.
Yes, sir. Very small.
So this quantity you can ignore.
Yes, sir.
So what is your R test now? R test becomes G2 by, this is 2 by G02. So what is your R out? 2 R02. And what was your GM? You found out your GM effective has to be GM1 by 2. So this connection V1, V2, and here your V out. Your V out is nothing but minus GM1 times GM1 by 2 times 2 R02 or R01 in that matter times your input voltage, right? This is V1 minus V2. So it is what? It is nothing but GM1 times R out times V1 minus V2. So this is a common source amplifier with V input is equal to V1 minus V2 and your GM effective is equal to GM1 by 2 and everything else is same. Okay. So now you see in this case this I1 minus I2 is coming out of this configuration and that is GM1 by 2 times V1 minus V2. So if I draw a fresh picture, so you have so far this is I0, this is V1, this is V2, and you had here I naught, right? I naught by 2. So this was your I naught by 2, this was your I naught by 2, and you had here I1, you had here I2, and this current flowing out, if this is short circuited, this current will be your I1 minus I2, and that has, we have seen that GM1 by G2, GM1 by 2 divided by V1 minus V2. Okay.
Yes, sir.
So now this one, can we double this current? That means what I mean to say, I have got I2 here, right? So can we somehow make this GM1 times V1 minus V2? Anything that comes up in your mind?
सर अभी तो बता दे करंट मिरर यूज कर लेंगे तो करंट
करंट
डबल हो
मिरर
जाएगा
यूज करने में क्या होगा आपका?
एंड डब्ल्यू बाई एल का रेशियो चेंज करके स्वाइस कर सकते हैं करंट को
So if you call this current as I, so this is I, this is going I. So if you add I here, so this I, okay, just let me use a different symbol. If you use I here, so this I will pop into here and this will become 2I. So this can give me this solution.
Yes, sir.
So this current, do we have it anywhere in the circuit? We have it in this branch. So we have to somehow use a current mirror to copy this current to the other branch. And the way we do it is, so this is your V2, this is your V1, and this is now your V out. So this current is now I naught by 2 plus I. This current is I naught 2 minus I, or let's say I naught this way, it is I naught 2 minus I. This I naught 2 plus I is flowing through this also. This gets copied here, I naught 2 plus I. So this plus I and minus I is going here and flowing 2I. Okay.
Yes, sir.
So this is how the differential pair works in this case. Okay. Now coming back to the, yeah, one more thing. What about the R out now? So we have made our GM effective as GM1. Is this clear? How did we make our GM effective equal to GM1? Earlier it was GM1 by 2, right?
Yes, sir.
By pumping in another plus I from the top side, we have made this GM effective as GM1. Now I need to check my R out also, right? Because that will give me the gain of the transistor.
Yes, sir.
So how will you check the R out? So R out of the differential pair. So you have what? You have this transistor. Let's say you have something like this. So this is your M1, M2, M3. This is M4. So you have your output resistance here, G03, G04, G02, G01. So you have to ground all the sources, and now you have to apply V test here to check. So this is your I test. Okay. So let's take this is your I1 and this branch it is flowing I2. Okay.
Yes.
So can you tell me where this I1 is going? This I1 is going at this place. This I1 is going at this place also. Can you see
Yes.
that?
Yes, sir.
Okay. So now this I1, what will it see? And this is also your small signal ground. So this I1, that means at this node, what is the input resistance? Again, the
GM
same question. 1
GM
over
parallel
GM,
to R not.
GM parallel to R naught, but we can ignore this thing, right?
Yes, sir. That is
Because this
very
will
high.
be very high.
Yes, sir.
So now what do we have? So if you simplify your circuit, you see what? You see your GM3 here. That means if I just look at this, so this will be this, then it will be another one, then it will be your GM3. GM3 it will see, and then this is your M1, this is your M2, and this is your V test, and this is your I1. G02, G01, this is grounded, this is grounded. This is looking from this to the, looking from this to this entire stuff. Please see if you have understood this.
सर करंट डिवीजन नहीं होगा
Which
M3 की
place?
तरफ I1 I1 will go through M3 and M4. नो
M4
सर नो सर नो सर ठीक है
वो
ओपन
गेट में है
सर्किट
ना?
होगा गेट में है ओपन सर्किट होगा
Yes. So there is no current here, here. So you are seeing this contraption, right?
यस सर
Okay. And what about if you look through this upside?
जी एम
So you are
M4
seeing this and looking here. Okay. So this is your V test and you are seeing I2 and there will be, and this is ground, this is M4. So this is G04. What is this current? Can I write this I1? This current I1, can I write this? Is it okay if I write this
यस
I1?
यस सर यू
Why?
कैन राइट बट साइन सर इट इज कमिंग डाउनवर्ड ना
No. Where is this I1 going? This I1 is going upwards, right? Look at this. This I1, this is the I1, right?
यस सर
This I1 is going through this, going through this, going through this, and going through this. So this will get mirrored. So this will be this direction.
यस सर
So it will be upward direction only, right?
यस सर
So now can we write I2 is equal to I1 plus V test times G04?
Yes, sir.
I can write. Let's keep this aside and now come back to this side. Okay. So can you tell me what is the thing you see beyond this? That means this is your GM3, this is your G01. So if I apply a V test here, so what should I see at my output resistance? So this is what?
GM1 in series with GM3.
GM1.
In series with GM3.
Again, just don't look at the circuit. You need much more practice. When you can, by just looking at the circuit, you can give out these statements. Okay, for example, this I test is flowing through this, right? So this voltage will be what? I test by GM3. This
Yes,
is your
right.
I test. So if this is your I test by GM3, then what is your I test? I test is equal to this is, by the way, your M1 transistor. So I test will be what? I test will be minus I test by GM3 times GM1, that is the current going this current, and plus it will be V test minus I test by GM3 times G01. So your I test will be 1 plus GM1 by GM3 plus your G01 by GM3, and it will be your V test by GM3. So this will give you what? This will give you GM3 plus GM1 plus GM3, GM1 times GM3, G01 divided by GM3. Is that okay?
Yes, sir.
So is my calculation right? This is I test. So this is your I test. This is your I test by GM3, that is gate minus source voltage times the GM1 of this, and this is the V test minus I test by GM3 times G01. Okay. So now you take this one this side, GM1 by GM3 and G01 by GM3, and this side will remain V test by times G01. This will be V test times G01. V test times G01. So if V test by G01, so it will be 1 over V test by I test will be your, this quantity is very less, so you can almost ignore this. So this will be your GM1. This will be your 1 plus GM1 by GM3 divided by G01. So I think I have made some mistake. Let me just recalculate. So if you have made that, it will be GM1 times, it will be your GM1 times V test. So this, the issue is here. This is your source voltage. So you have your I test equal to GM1 times V test plus V test minus I test by GM3 times G01. So if you do the simplification, I test plus G01 by GM3 times I test, and here if you do V test GM1 plus G01, so G01 you can ignore, so this quantity you can ignore, so you will have your V test by I test is almost equal to 1 over GM1. Okay. So now if this is 1 over GM1, 1 over GM1, so you can simply have this as your V test. Now this is your ground. This is your G02, and this will become your 1 over GM1. Okay. So we have broken the circuit down till this point. Okay. And now this is your I1. So if you calculate your I1 in the same manner, you will find that your R1 is nothing but, so this contraption have we seen earlier? This kind of contraption? Yes. This gives you nothing but V test times G02 by 2. So now what do you have? Your I test is equal to, this I test is equal to sum of these two. So this is I1 plus I2. So what is your I1? V test times G02 by 2 plus I2 is your, what was your I2? I2 was I1 plus V test times G04. That means this times 2 plus V test times G04. So your R out will be equal to G02 plus G04. That means if you draw the entire stuff now, this is I0, V2, V1, M1, M2, this is your VDD, M3, M4, and this is your V out. So your V out will be minus GM1 times your R out is divided by G02 plus G04 times V1 minus V2. Okay. So this G02 by G04, how have you calculated? You have calculated your R out of the differential pair. You split it in two component I2 and I1. I2 you have found out this. I1 you have simplified this contraption and then start looking into each transistor. Below here you have seen GM3. Now you have seen here. So you have simply again applied a V test at this point, then checked, again simplify this entire circuit to this. This is your M2, and then you have calculated your I1 to be this, and finally your I test is I1 plus I2, and you have found out your R out to be this. So basically, what is your R out? R out is nothing but this transistor's output plus whatever you have seen above, the output transistor, whatever you have seen above. Now in our circuit, in the main question, we can analyze one additional block is one block is additional. Let's say this additional thing is there. Otherwise, everything we have analyzed in this question. So how to take care of this? This is nothing but your cascode PMOS on top of your NMOS differential amplifier. So what you will see, this is your R06 and this is your R04 and this is your R02. Fine. And this is here where you are probing the output. So your GM equivalent will remain your GM1. You can follow the same process and see that your GM1 will only be the GM equivalent. And what about your R out? Your R out will be 1 over G02 plus, means this side plus whatever is above. Your above, in case of cascode, you know that your transistor, your output resistance becomes amplified by the gain of the lower stage. That means it will be your GM4 times divided by your G04 times G06. Okay. So if you simplify that, you will see this is coming out to be your output conductance. So let me just show you for the completion how you can calculate the, so output impedance of a cascode pair is that, that means you have so far this, right? This was given, so this was your VDD. Now this will be 0 and you just short your input and you need to see what is your R in. Okay, so you connect your V test here. This is your M4, this is your M6 and this is your G06, this is your G04. Okay. So looking above, you will see what? Your source and gate is grounded. So this is almost as if not present. So this equivalent circuit will be something like this. And this is your V test, and this is your G04, and this is your G06. So you can easily calculate what is your I test and get the relation. You will see that your V test is coming out as I test time GM4 over G04 times 1 over G06. Okay. This you can do easily. I just needed to show you the important step, this to this. Otherwise, you can do it easily. You just need to find out this voltage, and this you know will be your I test over G06. Again, following the same analysis, this Vx GM4 times Vx will be flowing here, and V test minus Vx times G04 will be flowing here. You can find it this. So this will be your output impedance, which will come into parallel of this. Instead of G04, now you have this thing. Okay. 1 over GM4 by G04 times G06. Okay. So this is how you calculate that your differential pair, and you analyze from scratch the entire thing. Okay. So okay, today we have exceed the limit by a long time. So let us finish here. And also, if you have any doubt, you can ask in the comment section, or you can just go through the analysis again. So you will be able to get whatever we have discussed. Okay. So let us close the session here.